Chapter 24, Molecular Structure and Energy Levels for Polyatomic Molecules, Supporting Information, Molecular Orbitals of Small Polyatomic Molecules, such as methane and water. So I want to show you this is the MOs of methane. The first four are occupied. These four are unoccupied. And the water, 1, 2, 3, 4. The first four are occupied by the 8 valence electrons, and these 2 are unoccupied. Now let's look at some molecular orbital coefficients, and we can analyze these numbers. So by doing computational chemistry calculations, we can get the molecular orbital coefficients for methane. So this is just the 1s orbital of carbon, and over here it's 2s orbital of carbon interacting with the 1s of this 4 hydrogen atoms. So you can have px over here, px interacting with this 4 hydrogen atoms. You can have py interacting with this 4 hydrogen atoms, or pz interacting with the 4 hydrogen atoms. So this 10 electrons in this CH4 molecule occupy the first 5 molecular orbitals. This 4 molecular orbitals are empty orbitals. I want to show you the interaction here. 2py interacting with the 4 hydrogen atoms, 2px interacting with the 4 hydrogen atoms, and then 2pz here. These 3 are degenerate. Okay, these 3 molecular orbitals have the same energy. This one, if you look at this one, it's the 2s orbital having destructive interference with the 4 hydrogen atoms. All right, so these 4 orbitals have higher energy than these 6 orbitals. All right, so that's why these 4 orbitals are unoccupied. And also pay attention to the gap between 3, 4, 5 and 6, 7, 8. If you look at the energy of molecular orbitals 3, 4, 5, it's negative 0.5 atomic unit. The molecular orbital energy of 6, 7, 8 is 0.7 atomic unit. And 1 atomic unit is 2,625.5 kilojoule per mole. So there's a very large homo-lumo gap. That means this methane does not conduct electricity easily. This is the picture. The 1s orbital interacting with the 4 hydrogen atoms. In this 3 MOs, it's one of the 3 p orbitals interacting with the hydrogen atoms. So if this is a z direction, you can imagine this is the pg orbital interfering with this 2 hydrogen atoms in a constructive manner, and also here it's also constructive interference. These 4 are higher energy molecular orbitals. They're unoccupied, these 4. So especially this one is really clear. You have a nodal surface surrounding the 2s orbital of carbon. Now let's look at water. Those are numbers. If you do quantum mechanical calculations, you can calculate the molecular orbital coefficients. So those are coefficients and the energies in atomic units. So now let's look at the coefficients. This is just the 1s orbital of oxygen. It's boring. This is the energy of the 1s atomic orbital. And now look at here. We have the 2s orbital from oxygen interacting with the 1s orbitals of the 2 hydrogen atoms. Right here, this is 2px interacting with the 2 hydrogen atoms. And this is also constructive interference. Over here, this is 2s and 2pz, so mostly 2pz interacting with the s orbitals of the hydrogen atoms. This is also constructive interference. So you have the negative lobe of the oxygen pointing toward the negative lobes of the hydrogen atoms. So that's why it's constructive interference. Over here you have 100% 2py. I think this is just the lone pair. There's no interference at all. These 2 MOs are unoccupied. Those are anti-bonding orbitals. This is mostly 2s interacting with the hydrogen atoms in a destructive manner. Over here, it's mostly just this 2px interacting with the 1s orbitals of the hydrogen atoms, also in a destructive manner. So now I'm going to show you the pictures of the valence orbitals. So this is the 2s orbital of oxygen interacting with the 1s orbitals of the hydrogen atoms in a constructive manner. So this is the 2px, constructive and constructive. But the signs of this 1s and this 1s are different. You can tell the different colors. All right. So this is 2px interacting with the 1s orbitals on hydrogen in a constructive manner. This is also sigma bonding. In this case, I think this is called 2pz. So 2pz, positive lobe, negative lobe. The negative lobe is interacting with this 1s orbitals in a constructive manner. So this is also bonding. Bonding. Lone pair. This is just 100% lone pair due to the mismatch of the symmetry. I think this is, let's see. It's 2py. Okay, it's called 2py here. This 2py orbital on oxygen does not interact with the hydrogen atoms at all. So this is 100% lone pair. Antibonding. All right. The order of the energies of this molecular orbitals is this. The most negative, and energy goes up here, lone pair, and then anti-bonding orbitals. The energy difference between this one and this one is called the homo-LUMO gap. This is the HOMO, and this is the LUMO. You can clearly see this nodal surface here and another nodal surface here.